All right, our exam has, looks like 16 multiple choice and 1, 2, 3, 4 free response. Okay? 16 multiple choice. All right. There are several things on here that you need to be aware of. Number one is that our sorry, my brain just went blank. There are a couple of types of problems on here that we haven't really discussed yet. Okay? Oh, you're not screwed. Yet. Not Thursday. Okay, that we'll need to talk about. One is a lab-based problem, and one is a graphing type problem. Okay? So we need to talk about both of those. So, let's finish up the stuff we haven't talked about yet. The last little bit from our thermo packet. And talk about heat engines and refrigerators in the Carnot cycle. That's the last little bit. We do not have any homework tonight, right?
Yes.
We do. Oh, that's number 7, right? We've covered most of number 7 except for Carnot, right? Okay, so it shouldn't be that bad because we've covered entropy already. So Carnot's pretty straightforward. Okay? All right, so let's cover that first. Get that out of the way. We'll talk about graphing problems in the test, and we'll also talk about like lab-based problems, okay? Because those will both show up on this test. I'm going to starting you off early with those this year, okay? Make sure that we're good at them, because they're showing up more and more on the exam. Okay, we're on page 11, I believe, in our What You Absolutely Have to Know About Thermo. Okay? And we solved a problem like this last time. And I left this one for you to go through for review. The one that we solved last time was one that looked like this. Okay? By the way, by what I've drawn, is it a heat engine or a refrigerator? Heat engine. Actually here, PV. Now it's a heat engine, right? Things that go around this way, clockwise, are a heat engine. Heat engines have negative work and positive heat. Heat goes in and work comes out. So it does work for us, right? If it goes counterclockwise, then it's a refrigerator. Okay, I forgot my D again. Refrigerator, and that will have work goes in to move heat out. Okay, work goes in to move heat out in a refrigerator. In a heat engine, heat goes in, and it makes work. It does work for us. Work comes out. All right. And in this particular one, we discovered that in these two cycles, in this one, I'm going to call this number 1. And actually, what do we call it? Where was A? Was A down here? No. A was up here. Yeah. A. So it went A, B, C, D. So in these two right here is where heat came in. Heat went in, so that was the QH, heat coming in. And in these two right here, in B to C and C to D, we discovered that heat came out, right? But you notice I drew a smaller angle. Not smaller angle, smaller arrow. So the heat coming out was less than the heat going in. And the area inside, that was our work, right? Work equals area. And that related to this diagram, our energy transfer diagram, where QH goes in, and then out comes work, and out comes the wasted heat. Okay? So that QH equals W plus QC. Right? And we said the efficiency of this thing was equal to the work that you get out of the machine divided by the total amount of energy you put into the machine. All right? What was our efficiency of this device? I don't remember. Is it 30? 25, 30? Was it what?
It was 27.
27? Yeah, it was like 20. I remember it not being that great. Yeah, around 25-ish. Okay, around 27% last time. Okay? And what were our high and low temperatures again? Remember? What was our lowest temperature, which was down here? The temperature at D was our lowest. That was like 60 degrees, was that right? Or 60 Kelvin? And what was our hottest temperature? Notes, 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 notes. You got notes? Oh, come on, we all worked out the temperatures.
1200 Kelvin.
What was it?
1200 Kelvin.
1200?
Oh, yes.
1200 Kelvin and 60. Wasn't it 60?
Yes.
Okay. I seem to remember 60. All right, and then we had a couple other temperatures in here. But this was the coldest, and this is the hottest that are hot, yes, 2 T's, that our engine ran at, okay? All right, before we talk about a refrigerator going in the opposite direction, let's talk about this 27% efficiency. That's not very great, okay? So the question came up because all of this thermo stuff here was all developed in the Industrial Revolution for the most part. And why was it discovered, or what was so important about the Industrial Revolution? What was the big change?
Steam engine.
The steam engine, right? Where they burn coal or oil or wood or whatever to generate heat. The heat generated steam. The steam pushed pistons that did work, like made trains go and factories go, generated electricity and all that sort of thing, right? So they're generating heat to do work. And so what became apparent to them is that they need this efficiency to be higher and higher and higher. Okay, because the higher this efficiency, the better their machine's going to run, right? And the less resources they have to use. Okay? So everybody in your packet, turn to page 15. Okay? The most perfect cycle that never was. Carnot cycle. All right? All right. The grand idea was that, well, why couldn't we make this thing perfectly efficient? 100% efficiency. And we talked about that last time. Why can't we make it perfectly efficient? Yeah, we can't get to absolute zero. Thank you. For one, we can't get to absolute zero, so that's a problem.
You can't make a frictionless machine.
You can't make a frictionless machine. Oh, yeah. Got it? And you can't get this temperature, or heat flows from hot to cold, right? Your ambient temperature outside, what the temperature is outside, limits how much heat you can have flow, right? You can't get below a certain temperature down here, right? Whatever the outside temperature is. So you have limits. So the question was, is how efficient can you make it? All right? And a dude by the name of Sadi Carnot, French dude, comes up with this idea that an engine that ran forwards and backwards, that could run as a heat engine or a refrigerator, forwards or backwards, and would have no friction, would be what we call a reversible engine, would be the most perfect engine you could get. You could run it forwards or backwards, it wouldn't matter. Okay? His reversible cycle has a couple of things. Number one is his cycle is frictionless. Okay? So there's no heat transfer during the mechanical operation of the machine. All right? Second thing is that the heat would transfer to and from the machine in an isothermal process, that there'd be no change in energy of the system, delta U. And I already told you the thing would work equally well forwards and backwards. And when he developed this cycle, the most perfect cycle that you could have, what he was aiming for was this. He realized that your engine is going to have to operate between two isotherms, okay? That you're going to have a hottest temperature and you're going to have a coldest temperature in the cycle. All right, now look at the one we have. Here's our coldest temperature down here on this isotherm, and here's our hottest temperature on this isotherm. Okay, look how much space it takes up. It takes up that much space between the isotherms, okay? And when he says, look, we need to fill up as much of that space as possible. So in order to fill up as much space as possible, he said, well, we need to have processes that are isotherms, okay, like this. And when we move between the isotherms, we have to do this with no heat loss. We have to be done as fast as possible. So that is that shape, which is an adiabatic. So what he has right here are isotherms. Isothermal process here. Isothermal process here. Adiabatic here. And adiabatic here.
Bless you.
I want you to notice, look at the green area. See how much bigger the green area is than our little box? And that's going to fill up much more area and have so much more work done for the same temperature difference. Okay? I'm going to erase ours. And if we could make our cycle like this. All right? Now, in this process, isothermal, delta T equals 0, therefore delta U equals 0. Therefore, Q equals negative W. Same down here. In our adiabatic, Q equals 0. Therefore, delta U equals work, right? On the adiabatic parts of the cycle. All right, so everybody, if this is going as a heat engine, clockwise, so we're going around this way, this way, this way, and this way. Okay? How would we figure out our work? How do you figure out work? It would be this area, right? Now, we're not going to be able to do that in this class, are we?
No, because it's calculus based.
Yeah, because it's not a nice trig or geometric shape that we can find the area for, right? That would require calculus to find that area. All right? So, that's our work, though, is all this area. Okay, where is heat going into and out of the engine? Where's our QH and where's our QC? Okay, if we label this one as, we'll label this as process number 1, number 2, number 3, and number 4. Where's heat coming in and where's heat going out?
Heat is in the board.
Where is heat not going in and out? Where is heat not going in and out? At the adiabatics. So 2 and 4, there's no heat. So Q equals 0. Q equals 0 here and here. So right here is my Q, is my heat going in or out?
In.
Which one? On number 3?
Let's do number 1.
It's going in.
Why is it going in? Rudy. Because work is negative going this way, correct? But Q equals, the heat is the opposite of the work, right? So we have heat coming in here. So this is our QH. And right here we have just the opposite. You have positive work, and heat equals the negative of the work. when they're in an isothermal process, right? So here's where the heat comes out. This is QC. So that's QH, that's QC, and that's the work. And again, QH, QC, and the amount of work that you steal, right? Got it? All right, through some math and derivation, which we're not going to do in here, we have that the efficiency of the Carnot cycle, of course, is work over QH. But for a Carnot cycle, there's a special new one, okay? Our special new one is TH minus TC over TH, okay? Where that comes from originally is work over QH, but work is equal to QH minus QC. And it turns out, because of the way our process is here, you can relate that to TH minus TC over TH, all right? That's the Carnot efficiency. That is the absolute best efficiency you could possibly have, operating between any two temperatures, all right? So let's go back. Let's go back to this one right here. We found out that our actual efficiency is 27%. All right? What would be the best possible, our Carnot efficiency, that we could have had between these two temperatures? It'd be 1200 K minus 60 K divided by 1200 K. The hottest temperature minus the coldest temperature divided by the hottest temperature. What kind of efficiency could we have possibly had? What is it, 95%? Yikes. 95%, and we're getting 27%. Not very good. All right, here's the deal. So why don't we build engines like this? Yeah, they're impossible. Why are they impossible? Well, number one is it's frictionless, right? So that's impossible for sure. So we're never going to get to 95%, but 95 would be the best we could possibly get between those temperatures, right? So we're going to get less than 95 just for friction alone. There's other practical reasons why you can't build this machine and it actually gets 95%. One of the main reasons is adiabatics work really fast, or they have to be really well insulated. Remember that? No heat transfer. So they have to be really fast, no time for heat transfer, or they have to be really well insulated. That's okay. You could probably do that. But isothermal is a problem for us. You remember isothermal processes?
They're very slow.
Yeah, they're very slow, and the reason why they're slow is because anything you do to a gas changes its temperature, right? And so the only way for the temperature of the gas not to change is for it to give heat off or absorb heat, and that takes time. So these are really slow and slow. So you have a fast process followed by a slow process. So what happens is, if you put this engine in your car, number one, it wouldn't be 95%. Number two is it would take you forever to get to school because it would run too slow.
Let's do it.
Okay? So you wouldn't really be able to use this engine for anything real practical. So why do we even bother with this idea of the Carnot cycle?
It gives you that idea of what is the most efficient machine going to be like, and
Sure, it gives you the idea of what's the most efficient you could shoot for, right?
although otherwise it's useless.
Yeah, otherwise than that, it really doesn't help us out. So, for instance, there's this idea that you could use the temperature difference that you have in oceans to run a heat engine. Like, for instance, the surface temperature of the ocean is different than the temperature down below, right? Down below it's colder, where up top it's warmer because the sun hit it. So, how great is that temperature difference? Well, the temperature up top may be 10, maybe 20 degrees warmer. Okay, so give me a rough temperature for the ocean.
70 degrees.
Okay, say 70 degrees. Okay, actually 65 degrees and below that, somewhere in the 60s is where you start to have hypothermia. It's really cold. All right, so like out in the ocean, you're talking 70. Actually, hurricanes occur when the ocean temperature gets above 80. 80, I don't remember if it's 79 or 82, somewhere in that range. So you can't have a hurricane until the ocean temperature gets to a certain level. That's why the hurricanes only occur after the summer, after the ocean has had time to warm up. There's enough energy then to generate a hurricane. So let's just make it easy. Let's say 80 degrees Fahrenheit, and then down here below is, say, 60 degrees Fahrenheit. Okay, now we need to convert these. Ooh, does anybody have a converter? All right, excellent. Can we convert these from Fahrenheit to Celsius? Actually, if you have an 89, you have conversions. Actually, if you have a TI 84, there's unit conversions in there too. In the apps somewhere.
Let me check. It's 26.67 for 80.
Okay, 26. Let's just say 27 degrees. Okay, what's it down here?
And it's 15.56.
Okay, so say 16 degrees. All right, now let's convert those. Ooh, I shouldn't have said that. What I should have said is, okay, if we build a machine that uses the temperature difference between these, so here's our machine. Machine. It's our heat engine.
Inside the water.
There's our heat engine. And our heat engine will work to create the heat flowing in from up here and heat flowing out down here. Heat flows from hot to cold and then will still work, right, in the process. That's what our machine will do. So the question is what's the efficiency of this machine? What's the maximum efficiency that this machine could ever have? Well, that's a Carnot question. So everybody calculate, what's the maximum efficiency this machine could have? Okay, did anybody get 41%?
Yes,
Anyone?
I got that the first time.
No, you messed up.
Okay, if you got 41%, what mistake did you make?
You didn't convert to Kelvin.
All right, these have to be Kelvin. So this is what, 300 Kelvin? And this is going to be what?
29.
To what?
89.
289 Kelvin. There we go. So once we convert to Kelvin, we have a temperature difference of what? 11 degrees up top divided by 300 Kelvin. Because if you use these two temperatures in Celsius, you'll get a difference of 11, which will be dividing by 27 instead of 300, and you'll get a much higher efficiency, right? Okay, so that's not right. That's a common mistake, which is why I wanted you to try it and make the mistake, because it's better to do it here than on the test. Okay, so I get like 3.7%. Okay, 3.7%.
I said 37.
3.7%. Wait a minute. Is that the efficiency that this real machine will run at? No, that's what? That's the maximum we could ever get, is a 3.7% efficiency.
This sucks.
Whoa! So is it going to be worthwhile to build this machine? Probably. Probably not. Probably not a good idea to build this machine, because we won't be able to get that efficient. So we're going to be talking about like 2%, 1% efficiency. Yikes. That's not going to be worth it. How can we increase the efficiency of this machine? How do you increase the efficiency of the machine?
Increasing the temperature.
Increase the
The biggest thing is you got to increase this difference somehow, or somehow or another decrease the hottest temperature, right? Usually it turns out that you're better off trying to get a bigger temperature difference here. That usually is the easiest of the two. So let me ask you this. So this one that uses what's called the thermocline, or the difference in temperatures between the surface and below, that's not going to be very efficient. How about though if you ran a machine that somehow worked on thermal vents? Like geothermal. Okay, geothermal, the steam vents and the hot water that you get underneath the ground, that's going to have a much higher temperature, right? And a much higher temperature difference. So you might have a better shot at efficiency there. There are some places that do that. What they do is like in Iceland, places where they have hot steam vents. They'll drill down into the ground and run pipes down in there, and the pipes run down close to where it gets really hot, where the ground is really, really hot. They'll run the pipes down, run water through the pipes. When the water comes out through the pipes, it's at a really high temperature. Then they use that high temperature to run their machine, and they get, better efficiency than that. Okay? Not as efficient as, say, like a nuclear power plant or a coal-fired power plant or something like that. However, it's free, right? Because the thermal energy is already there. So they don't have to, dig up coal, things like that, to make it run. So even though it's not that efficient, it's better than, using up all your natural resources. Here we go. Everybody, page 13. In your review packet. In your, what you absolutely have to know. Sorry. Okay, what the heck's a refrigerator? It's the reverse of a heat engine. Okay, and when I say the reverse of a heat engine, I mean the exact reverse. It does this. It goes backwards. It moves heat from a cold place to a hot place. And that requires work because it's unnatural. The math here is exactly the same. The heat that comes out into the hot place is equal to the heat that you removed from the cold place plus the amount of work you put into it. Did you catch that? So, here's your refrigerator in your house, okay? All right, you open up the door, you put some food in here, and your refrigerator takes out 100 joules of energy from the food. But it's plugged into the wall and requires 300 joules of energy to make that happen. So this is the QC coming out of the food. This is the work being put into the refrigerator to make heat flow in the opposite direction.
It's 400 joules coming out.
So what goes into your kitchen? 400 joules of heat. This is why your kitchen is almost, besides cooking, which warms up your kitchen, this is why the kitchen is almost always the warmest place in your house. Because the refrigerator and freezer is constantly running to get heat out of the food. It's a losing battle because heat flows from hot outside to cold, and so heat is constantly going back into your food, for which you expend electricity to pump the heat back out, making your kitchen hotter than it was before, making this transfer rate faster.
Is that why the outside of the refrigerator is hot sometimes?
Yes, so where is this hot place on your refrigerator? Okay, let's draw a side picture. Yeah.
Yeah, because when I get my cereals, they be extra warm.
And here's where the doors open. All right? And there's either going to be coils in the bottom or on the back of your refrigerator, which is why you're not supposed to shove them all the way against the wall, because you want airflow coming through here. You want a little air pocket for the air to flow. Okay, if you can, reach around and touch those coals or touch them from behind. Be careful, don't grab onto them, because they're going to be hot. Okay? They're going to at least be warm. All right? So warm air is always circulating out from the backside of your refrigerator. Okay? I opened the doors. And so here's your house. Okay?
Refrigerator.
And it's a really big refrigerator. And you put a fan in here, and you open up the doors, and you blow the cold air out.
It's Richard's refrigerator.
So does that cool your house off?
No.
No!
You're just wasting energy.
All right?
Like if you put your face in there.
Yeah, right here it cools you, but then you're generating more heat into the rest of your house, right?
Yes.
So by making this little area here cold, you make the rest of your house warmer still. So overall, the temperature of your house goes up when you do this.
Unless, of course, you put the fridge halfway inside,
Ah.
halfway out. That way the heat will.
So
go
here's what you do. You knock this wall down, and you do this. And there's your house.
Would that be
Now what happens?
It would be more efficient, but then your house would
You
get colder.
suck heat out of your house. QC. You put work into this thing with electricity, and you pump out the QH to the outside of your house.
I
Yes.
still think that would be.
And then it would start going.
Yes. This is what we call a window unit, right?
Yeah.
The air conditioner that you put in your window. Some of you probably have those. I grew up with one of those in my house.
They made those?
Yeah.
Yeah, we
It's a leak.
Actually, what we did is we just got an old refrigerator, duct taped it into the window, put a fan in it. That's called a refrigerator. Actually, it's called an air conditioner now, right? Because you're pumping all this cold air into your house, and so you live on the inside of a refrigerator. Nice. Okay? Works great. Hey, and if you don't believe that, wherever your air conditioner is for your house, if it's a window unit or if it's an outside unit that sits in the, like outside the house, it's the same thing. Except instead when it sits all the way out here, the pipes run to your house with the cold air, and it's technically like a coolant, and they do some magic work inside the house with a heat exchanger. There's two parts of it, okay? But there's going to be a unit either in the window or out in your yard, and when that thing's running, stand by it. What's it do? It's pumping out ridiculously hot heat, right? Even hotter than the air is already outside. Right? Even on a 105-degree day, that's hotter than that. Hotter than 105.
Unless it doesn't work.
Okay, so, but wait a minute. This works great in the summertime. But in the wintertime, you don't want this. So what you do is you knock a hole in this wall. You roll it over here.
Oh.
How do you roll a refrigerator?
Why don't you just buy
It's got wheels.
But now you have a hole in the other side of your house. You could just turn it around.
Or you could pull it out, turn it around,
It has
shove it back into the hole. One of the two.
And then you have two holes.
And now what happens is you take heat from outside when it's cold in the wintertime. You actually remove heat from the cold air outside. You plug it into the wall for work. And then what do you pump into your house? Heat. That's called a heat pump.
And it gets too
What
hot.
about your food?
What about you?
You have another refrigerator for that.
Yeah, I gotta have another refrigerator for that.
Then you make another hole in the wall.
You have another hole in your wall. By the way, this device that refrigerates your house and then heats your house, that is called a heat pump. So some of you have a heat pump at your house or apartment. It's a device that sits out usually in the yard, and there's tubes that go into your house,
Yeah.
and it runs one way in the summertime, and they switch. They don't actually run the thing in reverse. It always runs in the same direction. But what they do is they swap the way that the air is exchanged. And so essentially, it's like rolling the refrigerator to the other side of your house.
Without having
And then after you're cutting a hole in your house.
All right? The nice thing about a heat pump is, look, if you suck 100 joules of heat from the outside, and it takes 100 joules of work to make that happen, how much heat do you pump into your house? 200 joules. So you actually get more heat out than you put energy in. Nice. So a refrigerator can have an efficiency over 100%. The problem is that when this gets really cold outside, it gets harder and harder to suck the heat out of the cold air because there's not much heat left in the air, right?
So you use a lot of work.
So heat pumps work great where we're at because it doesn't ever get that cold in the wintertime. But if you lived up in Manitoba, a heat pump is a really ridiculous idea. Because what happens is that you can't get this thing to suck much heat out of like 0 or 20 degree below
Then you start a fire.
0 temperature. Yeah, and you start a fire.
Yeah, start a
Instead.
fire
Yeah.
outside right beside it, then it'll heat up there around it.
All right. What I'd like for you two to review is fill in the rest of this table on here. That's for you to fill that in. But a nice thing is that if you go to the very end of the packet, the back page is all the answers. Oh, that would help, right? Okay, so all the answers. So that'll help you work some more of these problems. Find the temperature, find the delta U, find the Q, find the work, find the efficiency of the device and all that. Now, don't do that now. You can do that at home. What I want to do then is review for the exam, okay? Now, those of you that have done e-homework or started e-homework, is there anything in e-homework number 7 then that you feel that I haven't covered or you have questions on? Actually, it turns out to be relatively easy. There's a lot of questions like this. A lot of questions, something about efficiency. And just remember, efficiency in general is work over Q. H, thank you. My brain just went blank. And then efficiency is TH minus TC over TH for Carnot. And you can set these two equal if you're assuming it's running at maximum efficiency or Carnot efficiency. Okay? And that helps you out with most of these. One last thing I want to talk about this efficiency thing is occasionally they'll say something like a power plant generates 600 gigawatts of energy. And they say the efficiency of the power plant is 30%. At what rate is heat generated inside the power plant to produce this amount of electricity? Okay.
So that's power of work, isn't it?
Yeah, so here we go. This is the amount of electricity generated by the power plant. So what is that? Is that QH, QC, or W?
W. Over.
Wait, it's produced though, it's the other way around.
Here's my power plant. My power plant generates electricity.
It produces heat also, taking in some heating units. It's W. Except it's going down
QH and QC, right? This electricity is the
power of work.
work. But the other crazy thing about it is giga. Okay, giga. What's giga?
6?
No, it's not.
Mega is
That's
10 to the
negative
6.
So it's 10 to the 9.
9, so it's 9.
10 to the 9th. Okay, no big deal. But that's watts. What's watts?
Work over
Joules per second. Okay, here's the deal. Joules per second.
multiplied by 9.
If I did this in units of joules over joules, would I get efficiency? If I did this in joules per second over joules per second, would I still get efficiency? Okay. So as long as you solve this in terms of power over power, or joules over joules, work over work, or joules over joules, or watts over watts, yes, temperature over temperature, you're going to get a unitless number here that's efficiency, okay? So this is our work. It's the rate of work. And when they say, what's the rate at which energy must be generated, heat must be generated to produce this amount of electricity, they're asking for rate at which, or the power, the rate at which heat is generated inside the plant in order to produce this work, right? So if you know that's 30%, and you know that the work is 600 gigawatts, you can find the rate at which heat is generated inside the plant, right? And it sounds really strange when they first ask you, but it turns out to be a really simple problem. So you would end up with an answer of something, 600 divided by 0.3. What is that? 2,000?
No, it's
Wait,
gigawatts.
Can you
But 2,000 gigawatts then, right?
Is
that right? Yes, 0.3.
Wait, is that 606?
600
700
gigawatts. Gee.
That'd be, our answer would be
2020.
QH equals 2,000 gigawatts. And you can leave it in gigawatts as long as you write gigawatts, right? It makes the math simpler. But make sure you put your proper units down, okay? There you go. Yeah, terawatts is next, right?
10 to the 9. No, 10 to 12.
Yeah,
Is
it's
it 12?
What?
After that, I don't know.
Right?
Okay, let's look at our review packet. I asked you to do one of these, didn't I?
No.
No.
You said the
Last
last.
page.
Last page, right?
What? The last page. Yeah, you said the last page.
The last
There,
page.
1200.
Only the last page.
700,000.
Very selective.
And then it was 24.
Oh, I see your hearing is very selective. Nobody did it?
I tried to.
I did the whole thing.
I don't know if I did it right. The last page.
Which, it was the last page? Front and back, or just the?
Front
I
end.
just did back.
Okay,
Front and back.
excellent. Well, let's take a look at it.
Well, you got that one.
All right? Let's look at, I think it's problem 85, right? This one right here. 85.
85.
Tell us, you said the last two questions.
The last two questions?
Oh, there were 3 questions. Sneaky, sneaky.
Oh, there were 3?
Ha ha. I didn't know that.
Okay, that's all right. Let's do the back page then. Do the back page, the one with the freezer. Okay, our first one then. You got 20 kilograms of food. So the mass of the food is 20 kilograms. Uh-oh, they got specific heat. 2e to the third joules per kilogram Celsius. By the way, everybody, you won't have to worry about specific heat on the exam, but we'll solve it real quick because it's easy. The temperature inside the freezer. Okay, the temperature inside the freezer, would that be TH or TC? That'd be the cold temperature, right? That's -5 degrees Celsius. Oh, I sense danger. Okay, so that's going to be Kelvin. What is that in Kelvin?
268.
68.
268 Kelvin. And then it operates for 10 minutes.
Change.
And
Mr.
it-
Bruin,
Yeah.
you really don't have to worry about it because it's specific to degrees Celsius, so you don't need to change either way.
Oh, yeah, you know what? Because we have a delta T.
It really does.
You're right, it won't make any difference.
-3.
All right,
T sub 8
10 minutes. I sense danger again.
600 seconds.
seconds.
600 seconds. Okay, actually just S. And then the temperature goes from this to a new temperature 1 to temperature 2 of -8 degrees Celsius, which is 265 Kelvin. All right, part A says, how much heat is removed during this time? Okay, Q equals MC delta T. Piece of cake, 20 kilograms. 2e to the third joules per kilogram degrees Celsius, and this is kilograms. And our delta T is 3 degrees.
Celsius.
Kelvin or Celsius, doesn't matter. Well, yeah, okay.
Celsius.
I'll do Celsius so that they cancel.
Yeah.
All right, we end up with 1.2 e to the 5th joules.
Do we leave it as that?
Does it have to be scientific notation or?
No, you don't have to put it in scientific notation.
No.
And as far as rounding goes,
I think 120.
Take off.
we're okay.
It's the same to me.
It's not a problem. That's a lab-based problem with data, like a data table. So we're okay.
We're cool.
All right? There's part A. Okay, part B, stuff that you'd be more interested in. The freezer operates at 400 watts. Uh-oh. 400 watts. What is that?
400 joules per second.
It's power.
Okay, that's 400 joules per second. But as far as what we've talked about in thermo,
Energy over
Heat.
Oh.
yeah, okay, that's a power. That's a joules per second. That's a rate of something. Is that? Okay, it's not P, it's not V, it's not NRRT.
WP equals W.
Is it QH, is it QC, or is it work? What gives it away that it's work?
It's delivered to the freezer. It's delivered into the freezer, right?
Operates that.
Right?
It operates at,
Because you know it's the electricity going in, right? Watts going in.
are you sure that's right?
Power is work per second.
All I know is work times time, so I just multiply power by time. 400 watts by time, that was it. All I did. I didn't even worry about all that.
All right. This is the work. It is the rate of work, right?
Yes.
Okay.
Is it okay on the test if we do like piece of W for power of work and piece of H for power of the
Yes, if you would like, actually, if this helps you all out, for our little energy transfer diagram, QH, QC, work, you can do it PH, P, and PC.
Yeah, that's
Or you just divide them by time.
yeah.
And that is the same thing, right?
Yeah.
Okay? All right, so part B asks, how much energy is delivered to the freezer motor during the 10 minutes? Okay, well, if that's the rate at which it does work, right?
Multiply by time.
I just, power equals work over time, right? Or the amount of work equals power times time, right? So it's going to be 400 joules per second, or watts, times 600 seconds. So we get a ridiculously large 2.4 e to the 5th joules. Okay? All right, so now, questions, comments? We okay? All right, part C then. It says, during that time, how much total heat is ejected into the room? All right, let's draw this properly then. Let's draw our refrigerator. Our refrigerator looks like this. QH, work, QC. Which one did we just find?
That work.
That's this one, right?
And we found
2.4 e to the 5th joules. E to the 5th. They want to find out the rate at which heat is ejected into the room.
That's Q sub 8.
Is that QH or QC? QH. So we're looking for this. How do I find that?
Well, we know QH is work plus Q sub C. And we know Q sub C from part A.
Okay, we know QH equals work plus Q sub C. We know this one now. That's the question mark we're looking for. Do we know QC?
Yes.
Oh, from the first one, because that's how much heat has been removed. So this is QC.
But would it be negative?
No, it's all because these two going in equals that one coming out. Technically, what you would write is this one positive going in plus this one positive going in minus this one going out would equal 0. But we've moved it to the other side, so we're working with magnitudes. So QH equals 2.4 e to the 5th joules plus 1.2 e to the 5th joules, giving us a grand total of 3.6 e to the 5th joules.
6.
All right? All right. And there we go. And then after that, part D is just find out the temperature change of the room. That's another Q equals, in this case, it's NC, technically CV delta T. It's like MC delta T. All right? Did they give us a specific heat?
Yeah.
80?
700.
But I think
Specific.
it's
80
Oh,
is
they gave
mass.
us 700.
They gave us mass to be 80 kilograms.
Oh, they gave us mass. So they're solving it MC delta T then.
Yeah.
Okay. And they give us 80 kilograms for the mass. They give us a specific heat of 700. And our temperature change is unknown, but we know that's our temperature, right? I mean our Q going in. So we find our delta temperature to be 6.4 degrees Celsius. All right? Does that look right?
Yeah.
Okay, not too bad. Okay, so this is a refrigerator problem. Now, I will tell you that on the exam, parts that you will not see. You won't see that, so part D won't show up, and part A won't show up because they've taken those off the AP exam. This is a really old question.
Right?
But those are so easy. That's
I know.
Because that's, I know, that's the easiest part,
that would
right?
add points to our free response.
I know. Unfortunately, they took that stuff off.
You're just looking.
Yeah, that's on the chemistry exam.
They don't pay us.
All right, let's go to
So they're
the.
gonna give us malls or something? Or some other way to find it?
Actually, the only way we'll be able to find that with the information given to us will be through
No, I'm saying.
delta U equals Q plus W. That's our only real tool to find that.
If we actually did just use MCAT though on the exam, would they count it wrong?
No, if you have enough information, you can find it, get a proper answer, perfect.
So that's acceptable for free response as well?
They just probably.
So
What happens though is they generally won't give you specific heat, so you can't do it.
Right, but if you like,
Well, what do you
for
mean?
like water or whatever.
Yeah, if you have water memorized, now just remember for water, what's the specific heat for water?
4.184 kilo. I mean 4.184.
All this stuff's going gas.
Yeah, or 1 calorie.
1 calorie or 4 point.
1.1
Yeah, but that's for, not for kilograms.
Gram.
That's for grams. So how do I change it to kilograms?
Multiplied by
It'd be 4,100. Yeah. So just be careful of that. You won't ever need to use it really, but if you want to, you can. Okay, let's go to the page before. All right? Let's start at the top. Problem 85. It says you got 0.03 mole of a sample of helium. It's taken through the cycle that's shown. The temperature at state A is 400 degrees. That was nice of them.
Yeah.
Okay, this is exactly what we've done already. So fill in that table. It wants to know what is work, Q, and delta U, positive, negative, or zero. And I think on my handout, that's supposed to be a delta U, but I think, oh, it did show up right as delta U. Good. Okay, so fill in that table. Work, Q, and delta U, positive, negative, or zero. All right, what you got?
FE0,
This one? Zero? Why?
because it's subverted.
Because there's no area underneath there, right? No volume change. All right, what's... You know, this one's the hardest one to find, so why don't we find this one first, right?
Positive, yeah.
Okay, so this is positive, right?
Yeah. Delta
Because
Q.
you're going up in temperature.
So temperature is positive there.
And so those two, that has to be positive, because these have to be the same, right?
Yeah. Because delta U's you could keep as W.
Got it? Yeah. All right, how about from B to C?
Oh yeah.
Negative, because you're going to the right. You have because work equals negative P delta V, you have a delta V. You have a positive delta V, so therefore this is negative. All right, Q, from here to here. Well, that's the hardest one, so let's do delta U first. From B to C. Why zero?
Because it's on the isotherm.
Ah, 'cause that's what it says. It says isotherm. It says isothermal, so that's what it says. So that's got to be positive, and these have to be the same value, right? They have to cancel out to equal zero. All right. Okay, work from C to A. Positive, because you're going to the left, right? Since this is a negative volume change, you have a positive amount of work. All right, skip that one again. Go to delta U. Going up or down in temperature?
Down.
Down in temperature, therefore down in delta U. So this has got to be, yeah, it's got to be a real big negative, right? You don't need to put a big negative in there because it just want a negative sign, but it's got to be bigger than the work, right? Excellent. Okay, explain your response for the signs for process AB. Okay, how would you explain work equals zero?
Area.
You could say no area underneath the process or the line. What's another thing you could say? no change in volume. Therefore, work equals 0. I wrote work equals 0 because work equals negative P delta V, and delta V is 0. Okay, so you can do it that way as well. All right, how are you going to explain? That might be the hard one, right? So why don't we explain this one first?
Change in temperature.
Yeah. Delta U equals 3/2 nR delta T. And we're going to be moving up in temperature because we're moving up in isotherms, right? Or you could say PV equals nRT. You're going up in pressure while these all stay the same. Therefore, you have to go up in temperature. If you go up in temperature, you have to go up in internal energy. Okay? All right, which brings us to delta U equals Q plus W. If that's positive, and that's 0, then that has to be positive because those two have to be equal. All right? All right, and it says calculate volume C. It is on an isotherm, that's correct. So what does that tell us? Say that again? Ah, very nice. Since we're on an isotherm, that means delta T equals 0. That means P times V at A must equal P times V at B. Sorry, it's
B and C.
B and C. I got it backwards. B and C, right?
B and B.
The volume and pressure at B has to equal the volume and pressure at C, right? All right, so this one is 5 atm at 0.001, and this is at 1 atm at VC. So that's got to be 0.005 meters cubed. And you're done. Very nice. So it turned out to be a PV equals nRT change in state type problem, right? Because you go from one state to a new state. Okay? Very nice. Very nice indeed. Okay. What I'd like for you to do is to answer the last question on that page. All right. Heat engine operating between temperatures of 500 and 300 Kelvin, lifting a mass of 10 kilograms vertically at a constant speed of 4 meters per second. Part A, determine the power that the engine must supply to lift the mass. Okay, power supplied to lift the mass. So, what the heck? It doesn't sound like thermo to me.
You know, force going downward by gravity.
Yeah, how do we find power? What do we got?
Force times S delta V cosine theta.
Ooh, force times velocity. You could use work over time. You could use change in energy over time.
We're given the velocity.
All right? This is the one that gives you force delta R cosine theta over time, right? Where that's your velocity. So technically this is,
Delta V.
yeah, I've got a cosine theta here, right? So that looks like our best bet, right? So we've got the velocity. Lifting the mass. What force is required to lift a mass at a constant velocity?
The same force.
Oh, sorry, I have like my bad. Excuse me.
I'm sure they gave you
You got a 10 kilogram mass. How much force is required to lift it at a constant speed?
MGH, the same as gravity.
mg and mg, right? So that it moves up at a constant velocity. So our power equals mg times v, force times velocity. What about our cosine theta?
It's one.
Why?
All you need is
Because you're moving up and your force is up, right? So cosine between the 0 degree angle is 1. So there you go. So there's your power, mgv. But you got to plug those numbers in, I guess, right? What is it? 300 and what?
92.9.
92 what?
So watts.
Watts.
So we say 100 watts is
392 watts is our answer to part A. Okay, part B, determine the maximum possible efficiency of this engine. What did they just ask for?
What's your main?
What's
Yeah.
Yeah, there you go, the Carnot. Efficiency Carnot, that's the best you could ever get. TH minus TC over TH. Okay, whoa. Do we have to worry about, we okay?
Yeah, we're good.
All right, because they're in Kelvin, right? Okay. So we're going to end up with what? 200 divided by 500.
40%.
So 40% or 0.4. Either one is acceptable. Okay? There you go. Now it says if the engine were to operate at this maximum possible efficiency, determine each of the following: the rate at which the hot reservoir supplies heat to the engine, and the rate at which the heat is exhausted to the cold reservoir. So they're asking for QH and QC, right? But they're asking for them in units of rate, so they're asking for them in units of power or watts, right? So let's just draw our little diagram, our energy transfer diagram again, because we have a heat engine. QH, work, QC, do we have any of those?
Work.
We have this one, right? In units of watts, 392 watts. Okay, so how do we find the other two?
Efficiency.
Efficiency is work over QH. So that's 0.4 equals 392 over QH. And so now we have QH in terms of watts.
981.
What is it?
981.
981 watts. All right? And then QC is a simple matter to find because then we just, that one minus that one's got to equal that one, right? So what goes in equals what comes out. And 589.
980. I use 91.
Now that's off by one. It makes a difference.
It's supposed to be
Is that right?
Yeah.
No?
No, it's off by one.
It's
No,
980 watts, not
So it's
91.
off by one.
So it's 588.
Oh, this is 980? All right.
One significant.
Goodness gracious. Well, heaven forbid.
I could have.
Within rounding, we're all good. Okay, there you go. Okay, so should you be intimidated by heat engine or refrigerator problems? No.
Very much so.
No, it's not this. Yes. No. Oh. These are not hard. Just remember, draw your energy transfer diagram, and then write your efficiency equations. Piece of cake. Should you be intimidated by PV diagrams? No. No.
Right now.
Somewhat.
You can do it. Okay, I want you to turn to the very first free response problem. We need to go through this one. Yeah, this is a fun one. Fun meaning fun and challenging and fun.
And then you don't know this.
James Bond must to establish the value of.
All right. It says, is this one right here? All right. Oh, you didn't focus it? Come on. Got it? All right. It is you are given a cylinder of cross-sectional area A containing n number moles of an ideal gas. Okay, before we even start, what does it look like? Does this look like a heat engine problem? It looks like some sort of PV equals nRT type of problem, right? Yeah, you heard moles of gas and you're like, uh-oh, PV equals nRT somewhere, right? Okay, the piston fitted closely in the cylinder is lightweight, so no mass, and frictionless, yay. So it's an imaginary, frictionless, massless piston of science. The objects of different mass, m, are placed on top, as shown in the figure above. In order to determine n, the number of moles, you perform an experiment. Because we don't have a molometer, right? That we can plug in there and measure the number of moles. All right, you keep adding more masses, 1 kilogram at a time. You measure the volume. All right, and you allow the thing to come to room temperature each time. Whoa, whoa, whoa. You allow the thing to come to room temperature each time. What kind of process is it?
Isothermal.
Isothermal. Okay, so you're keeping it the same temperature, but you measure the new volume. And they give you that data table. Uh-oh. Ding, 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 ding. Data table. What does that tell you need to be careful about this time? Units and significant figures. That thing that goes with units. Nice. All right, you got to make sure that you are consistent with significant figures. So how many sig figs should our answer have? 2. All right. Okay, notice that in this diagram, or in this table, they have mass, they have volume, and then they have 1 over volume. We're going to talk about that in just a minute. All right, it says write the relationship between total pressure, P, and volume in terms of the given quantities and fundamental constants that would allow you to determine N. So what is our governing equation that relates all these things? PV equals nRT. You know what? You just got a point. You just got 1 point out of 10. They gave it to you.
Happy face.
Yes, happy face is right. Okay, mass 0, 1, 2, 3, 4. Volume in meters cubed is 6e to the negative 5th. I'm not doing sig figs up here just for time. 4.5 e to the negative 5th.
3.6.
3.6.
2.6.
And then 1 over v, notice the units, 1 over meters cubed, or actually they write it meters to the negative 3rd. Okay? So 1.7 e to the 4th, 2.2, 2.8, 3.3, and 3.8. All e to the 4th. Okay, there you go. And we just saw part A. Part A, the answer is PV equals nRT. Yay, go team. Okay, now, you also determined that the area is, okay? So you know that the area of your piston is 3e to the negative 4th meters, and that the temperature is 300 Kelvin. Calculate the value of P for each value of M, and record your values in the table above. All right, so everybody do the first 2, and I'll give you the rest. Uh-oh, I've sensed a problem. I hear several people saying, well, I'm going to use PV equals nRT. Because I know V, and I know R, and I know T.
We don't know the number.
Oh, but we don't know N. So, you know what? There's nothing wrong with just doing that, except that you just can't get there, right? Okay, so back up the truck.
I didn't even try to use that.
How else can we get the pressure?
Force over
Area plus 1 ATM.
Ooh, okay, here's the deal. The pressure in the gas is going to equal this force over the area right here, right? This force is going to be mg over the area, right? But if you just do mg over the area, that's not it, because what are you going to get for your first pressure then?
Whatever is
Zero.
You're going to get 0. Whoa, your gas has 0 pressure in it. Danger, danger, caution, caution. That should set off a little alarm in your head. That doesn't make sense.
100,000.
All right? So, what did we forget?
Add
We forgot that there's 1 atmosphere pushing on the top, which is 100,000 pascals. So our first one is 100,000 pascals.
You use one of
Mr.
those.
Brewer,
Yes.
so we use 100,000 on these questions because on the homework. we
Very
actually
nice.
use-
Excellent question. The question is do we use, what number do we use for pressure on here? Now on the e-homework we had to use 101,325 because the computer doesn't know enough. When you're off by 1% or more, it counts it wrong.
It's stupid.
On the AP exam, they allow you to use this, so it simplifies the math, particularly on multiple choice. So let's just use this. That's on your constant sheet is 100,000. Good question. All right, so what's our next one going to be? Well, it's going to be 100,000 plus this.
1 kilogram times 9.8 divided by 130.
And it ends up being something like 130,000.
Yeah.
Okay, those of you that put something other than 130,000, you're going to lose a point. Why?
Significant digit.
2 sig figs. Right? 2 sig figs. So you need to use 2.
The first answer only has 1.
1.0 times 10 to the 5th. That's it.
All right, smarty pants. 1.0 times 10 to the 5th pascals. That is correct. Thank you for keeping us honest. Okay, you can figure out the rest of these then, right?
Yes.
Okay, we can do that. Because the pressure in the gas is going to equal the mg over A from the mass plus an atmosphere. Now wait, I'm not done. You can't put up. It says then, plot the data on the graph. P times 1 over V. Why did they do that? 1 over V.
Because they want us to do it.
They wanted to be
PV equals nRT. Hey, pay attention because you'll need this.
P equals 1 over V.
This is on your y-axis, that's on your x-axis. P equals nRT times 1 over V plus 0. Y equals mx plus b. That's your x-axis, that's your y-axis, that's your slope.
Nice.
Everybody, please be careful. You got to graph this stuff.
So what
Do your best fit line. Eventually it says,
calculate?
from your graph, find the number of moles. Hang on, sit. Listen. If you do this and go up and over and find 1 data point and take your 1 data point, plug it in here and find your number of moles, you won't get full credit because you haven't used all of your data. What are you supposed to do?
That's fine, but
Use the slope of your best fit line, and your slope equals nRT. So whatever your slope is, solve for that equals nRT. Does that make sense?
Yeah.
Because that is the best use of all of your data. Okay, we'll talk more about that later. Okay, test next time.
It also